Okay, welcome everybody. We should get started. This is going to be an exciting session about an exciting topic. Summary, a collision of two beautiful technologies. And we're working together to try to see what we can do about coexistence. Anyway, so I'm just going to open up with a very brief introduction to some of the problems that low Earth orbiting satellites in particular pose for us. In the background is a Subaru image with a satellite crossing it. And I should point out Rachel Street sitting right over here. She's my co-chair, our co-chair, and she's going to be monitoring the Slack chat channel. So if you have questions out there, please put them in there, and she'll rattle our cage and bring them up in order. There are microphones here, and we will have. Please do not in the room speak without the microphone, because there are a lot of people out there in the Zoom land also tuned in. And I think we have proven, if somebody else out in Zoom land can say hi for an audio test, I think we're good to go. Can you hear us?
Hello.
Yeah, we can.
Okay, cool. All right. So second slide. This is a slide from Satoshi Mizaki of a Subaru HST exposure made in March in the G-band. 50-second exposure, and you can see a couple of satellites. Actually, you can see three if you look very, very carefully. There's another one right there. It's a 1.5 degree field. LSST has a 3 degree field. This gives you context. There are going to be many more satellites launched. This is with the existing roughly 2,000 satellites that are there. They're going to, say again? 5,000 now. Thank you. And they're going to be an exponentially growing number of them, up to as many. Meredith is going to give us a summary of this, but up to maybe 100,000 or so. So that's one context. Here's another cool, interesting one I got recently from a observatory up in Canada. They were looking at M3. The way they did this was they had 166 1-minute exposures over 2 nights. This is a 4 degree field. Remember, ours is 3. But if you do the math, this was taken before these data were taken before COVID. So the number of satellites up there was quite limited. If you do the math, this is what we're going to have about 1 or 2 of these in each exposure with LSST. Each exposure, in other words, it's not going to look this bad, but it's going to have 1 or 2. And if you try to combine them, it'll look this bad. So one of the issues that we have, and we've got a couple of posters out there, is the crosstalk between amplifiers on each individual CCD has 16 amplifiers, because we were forced to split them up into 16 pieces so we could read the focal plane out in 2 seconds, if you heard Aaron's nice talk earlier. And what you see in this image is the main satellite streak. This is done in the lab, by the way. And the first order crosstalk from one amplifier talking very weakly to the next one. By that, I mean like a few parts in 10 to the 4. And then you can see the second order and the third order. So this is an issue, and the way to solve this issue, the most direct way to solve it, is to make the satellite fainter. If you make it faint enough, then we feel, and there's a couple of posters like I'll mention in a second, we feel that we should be able to correct for this to first order for all 189 science CCDs, but it has to be fainter than about 6.5 G magnitude. And so, speaking of posters, here's a poster that talks to that, led by Dan Pullen, that's out there. And the CCD is split into 16 sections. The upper 8 is shown on the left. and the lower 8 is shown on the right. And what is plotted here is the crosstalk coefficient from that main trail to the next nearest neighbor. You see the crosstalk is low. These numbers are like where my cursor is 0.0003. And you see there's a difference in behavior, but the thing that should catch your eye is that these are not flat lines. The crosstalk coefficients depend on the luminosity, depend on the satellite streak's peak brightness, which is down here on the lower, on the x-axis, going from 0 to 120,000 electrons. So we have to characterize this for each one of the CCTs because they're all different. And in fact, all 16 channels are different and all possible combinations of amplifiers on a single CCD are different. Long story short, there's about 500 million observations on sky you need to calibrate this effect. That's 1 month of observing. So in principle, we can do this. So that's one poster, it's out there. But this assumes we can correct to fainter than 6.5 G magnitude. This is another poster which should probably, in view of what I just said, alarm you. Fan Kadula has run a program that Forrest Fankhauser wrote, and you're going to hear Forrest talk about his satellite brightness prediction algorithm in a minute. On a fake, this is a complete end-to-end simulation. The only real data it uses is the reflectance data in the lab from SpaceX on V1.5 satellites. So we have that data. Combine it with a data that with a database that was developed for scheduling LSST for 10 years, predicting the brightness of satellites. And what's plotted here on the bottom is you can predict the number of LEOsats in magnitude bins. These are half magnitude bins. On the left is an average summer night during the beginning of the night. And so +1 hour past first observation is just past -12-degree twilight. These we all expected, but who ordered all this bright stuff? Same problem emerges at the end of the night at sunrise. And that's at +7, +6. These we expect over here, but who ordered all these bright satellites? And so we have a bit of work to do to understand the origin of this. But this is the first time we've ever tried to do a full end-to-end simulation of the issue. Okay, so you can go and see those posters. There are therefore several mitigation challenges. There are the streaks themselves. There's this nonlinear crosstalk I mentioned, streak masking residuals, and you're going to hear from Adam Snyder at the very end about that. Variability in glints. The streaks are not constant in amplitude. They move around. And in fact, what I should have done, and I'm going to go backwards here, is to show you something curious in this image right there. That's a satellite that is glinting during one of those 60-second exposures. Variability in glints, bogus events that are caused by that, and the science impact simulations. And so for the first time, we have begun to do science impact simulations, and there's you're going to hear a little bit about Erfan Nurgabov's work on that from the last talk with Adam Snyder. So here's the agenda, introduction, which I'm finished with, overview from Meredith, who will come up next to give you the background on all of this, regulatory considerations from Ashley Vanderlee at NSF, Starlink constellation update from Goldstein, SpaceX, predicting optical satellite brightness from Forrest Fankhauser, and the streak masking challenges, followed by a discussion. which will be lively and a lot of fun. Remember, respect. So we have to respect our colleagues. Anyway, so at the end of each one of these presentations, we have a tiny bit of room for an urgent question, like, what did you mean by? But the real discussion will be during the discussion period. So Meredith, why don't you come up and lead us off? Let's see. I've got to get out of this and start this. And somehow I've got to go to full screen.
Oh, you already got the second tab.
So yeah.
Go to this arrow.
Okay, thank you.
And then presentation mode at the top.
Gotcha. Now I know how to do this.
And then you should be able to click the more, and it should auto hide. We don't know why it doesn't auto hide. Hide floating V controls.
Oh dear. Okay.
And now that should go away, and then advancing will be the arrows.
Thank you much.
Good.
All right, thank you, Tony. And now we all know how to use Windows to advance the slides, so we are all in business. Thank you for the introduction, Tony, and thank you all for coming here today to hear about the latest with Rubin and satellite constellations. So Tony already gave a little bit of motivation. I want to step half a step back, give you a little more context for kind of what's happening in low Earth orbit, why we care about this with Rubin from a Rubin perspective. And I said that I knew how to use this, and then it didn't want to advance my slide. There we go. So the situation that we're facing is that while light pollution across the Earth has been not a new thing, there is now a new source of globally visible light pollution. We can't just go to a more remote site harder and hope that things will not build up near us, because the satellites are going everywhere overhead. There have been over 4,400 Starlink satellites in particular launched since 2019. And I believe a keen audience member pointed out that there are now over 5,000 satellites, not all Starlinks, but 5,000 active low Earth orbit satellites. And so Starlink is more than half of the population at the moment. It's the majority of the yellow bars that you see up there on that slide. SpaceX has provisional permission to launch over 40,000 satellites. Whether or not that actually happens, stay tuned. Life comes at you fast. And there are many other companies that would like to do a similar thing. This is not, at the moment, SpaceX is one of the biggest players, but they are almost certainly not going to be the only player during the time period of Rubin operations. So we are rapidly heading toward an era of tens to hundreds of thousands of low Earth orbit satellites, and we're going to need to deal with this. So I want to talk briefly about how we can kind of quantify the impact on Rubin science, with a partial credit to Željko, who put together kind of this framework for trying to assess exactly how we can come up with like a quantification for this. Because waving your hands and freaking out about the numbers is fun to a point, but you need to at some point actually sit down and put some numbers on it all. So the challenge here is that it depends on several imperfectly known quantities, right? If someone could tell me with certainty how many satellites there are going to be in low Earth orbit in like 5 years, that would be great. Feel free to talk to me after the talk if you know that number. Satellite brightness distribution, also big unknown, a lot of work happening in that area, but whether or not everyone is going to follow the best practices that are coming forth, how many satellites are going to glint weirdly, how the LSST camera responds to this. Tony's group is doing amazing work in that department. And then finally, the image processing pipelines that I'm on the alert production team for the science pipelines, and part of what we're thinking about is how we're going to handle that. So, okay, so to break it down, first of all, the number of satellites in their orbits. This this image here came from a recent New York Times special that actually it's animated. If you go look at the real article, it's kind of cute and kind of terrifying. It's a projection, right? So this may not be the reality necessarily. It's based on filings from all of the different companies listed down there, and it's kind of where these companies would like to see us headed, because you can get global coverage if you have a bunch of these low Earth orbit satellites. They're not very high up, so by definition, you need a bunch of them if you want to be able to have a constant internet service available. But what that means is that they orbit Earth about once every 90 minutes. So they're going real fast. And at any given time, only about 4% of them are actually visible above the horizon. And at any given time, less than 1% of those are at a high altitude in the sky. So if Rubin is doing most of its observing, like kind of more zenithy versus like horizon-y, then you're not going to be affected as much as if you were doing really higher mass observations. There's exceptions to every rule, but that is at least somewhat in our favor. My best guess for the total number of satellites in the next decade is somewhere between 50 and 500,000, because what's an order of magnitude among astronomer friends? But where we land in there really remains to be seen. It depends on a lot of factors outside our control that we're going to hear a little about later: economics, regulations, different companies, priorities, et cetera. And the actual physical carrying capacity of low Earth orbit is also not really well understood. There's folks working on the space situational awareness area to try to understand this and come up with ways to model it. When does it all become a debris problem, et cetera? I'm not going to go into that either, but that is another area of active research. So very much a stay tuned kind of situation. Now, that being said, lower altitude orbits in some ways are better because the satellites move the heck out of the way quick. They don't linger and leave a super high bright streak on your detector. And they're also more out of focus. So your peak brightness, which is one of these critical things for correcting the crosstalk that Tony was talking about, that's a little better if it's a broader streak with the brightness spread out over a larger surface area. You also get somewhat fewer satellites that are illuminated in the middle of the night during the summer if they're at a lower altitude. However, you're going to inherently have more the lower you go. So that is an inherent trade-off. And also, a lot of the plot I'm showing here that kind of gives you an idea of how many of the observations Rubin would take that would have a satellite in them. The worst situation there is a reality with 48,000 satellites, total population. And at twilight, right, almost all of the exposures would have at least a streak in them. Whereas at a smaller constellation, the orange, only 12,000 satellites, only about half. And then if you look at midnight instead of twilight, the situation is better. At certain times of the year, it's actually nothing, which is a benefit of being at a nice low latitude. If you have a telescope at a higher latitude, like some of our Canadian colleagues are like to point out, excuse me, like we have telescopes too, and this is also a problem in a slightly different way depending on the latitude. So lots of trade-offs to consider. This is a plot from Samantha Lawler's paper that came out last year, and it shows kind of this trade-off from the latitude thing. So when we're thinking about how to optimize for Rubin Observatory, I encourage folks to think a little more broadly about other observatories too, because obviously Rubin is really amazing and important, but we need to be careful that the recommendations that we're making are not just going to make things fine for us and kind of leave everybody else in the dust. All right, that was the how many and like where in orbit are they? How bright are they? So there's no rules limiting satellite brightness at present. As Tony said, a D-band magnitude of around 7, maybe 6.5, somewhere in there, would both render them basically invisible to the unaided eye and would mitigate a lot of the bad effects that the crosstalk that he was talking about as well. There are lots of darkening mitigations that are happening, but they're not quite at this target yet in a consistent way. So lots of positive developments in that direction, but active changes happening. On the right here, I'm showing a plot from a paper that I really hope is going to show up any week now. We've resubmitted a bunch of times with a big group of folks from all around the globe who took observations of this new Blue Walker 3 satellite. And there's only one of it. So at first you might be like, okay, well, one thing, whatever. But it is a football field of reflectivity. And if you look at the y-axis there, it's not like the data points are not around 7th magnitude. The data points are around like 1st magnitude. This thing is honking bright. So it was a kind of a test for a direct-to-satellite or cell direct-to-satellite thing, but they want to launch a bunch of them, and this was their first. And that would be bad if that happened. We would need to probably avoid that with Rubin, which would be feasible to a point. But we need to keep an eye on some of these weird one-off things that, again, it's not just one company that we need to be paying attention to. In addition, it's important to consider that this idealized operational or on-station magnitude is not the reality for the entire life cycle of a satellite. They have to launch and get up to orbit. And then they have to deorbit eventually, and they do weird maneuvers sometimes because they do require solar panel orientations to get their power. So sometimes they will glint, and here's some examples from the Zwicky Transient Facility that saw a bunch of glinting satellites. We're gonna see these in Rubin too, and we're gonna have to deal with them. All right, I'm gonna kind of gloss over the camera because I think we're gonna hear more about that later. It's very sensitive to bright things, can cause some issues. We're working on it. Ask people, not me. Go to Daniel's poster, etc. But what we can do is point it at different directions. And I was on a study that looked into this, and it is indeed technically feasible to dodge regions that have the highest satellite density. So that's heartening. And if we do it, it costs about 10% of the observing time in order to have about half as many streaks in your image. So we need to be in a situation where there's enough potential science loss that we're okay sacrificing 10% of our observing time to mitigate that. And making that call is above my pay grade, but is a tricky thing that we're going to have to consider as operations gets underway. In addition, this simulation that we did assumes that we know exactly where everything's going to be, and that's obviously not right either. So we need to be sure that we can get some more accurate satellite forecasts if we're going to implement this kind of a dodging scheme. But it is technically doable, which is nice. So the image processing pipelines is kind of the last piece of this. And this is where I want to just let everyone know that you're going to find some streaks and glints and residual satellite bits in our data products. I'm sorry, we're going to do our best, but given the population that is likely to exist, we're not going to be able to get rid of absolutely everything. We do have a code that does a pretty good job of masking streaks in coads. You can read all about that in that tech note. That was Claire Saunders, my colleague, put that together. And then also Tony's team uses a similar technique. Adam Snyder can tell you more about that to find streaks in their lab simulated images. Soon, we're going to be adding the streak detection to our single frame processing pipeline as well, so that we'll be able to know like if just a visit level image has a streak or not versus just dealing with it at the coads when we're adding the images together. We still need to figure out how we're going to deal with the false positive glints at our alert stream. And then in the future, what I really like to do is use the satellite streaks that are going to show up in the data to then kind of make a feedback loop and to measure the impacts on science and use that to make informed decisions about if we need to adjust our survey strategy, if there's something else that we need to be doing algorithmically to get rid of them better, and so forth. Because we're going to have this kind of, we're going to have real streaks in real data, like it or not, that we should be able to then use to improve the situation for both our own science and hopefully for the community, because we're not going to be the only telescope on the ground trying to do science and seeing a bunch of streaks in our stuff. All right, so that's kind of how we can try to begin to quantify this. Maybe you are now agree with me this is a problem and you would like to help. Welcome. I would welcome that very much. There is one way to do this is there is this relatively new IAU center that I am co-leading the SatHub chunk therein. And it has a big mouthful of a name, so I apologize, but it is the IAU Center for the Protection of the Dark and Quiet Sky from Satellite Constellation Interference, or colloquially CPS. And this is jointly led by NORLab right here in Tucson and the Square Kilometre Array Observatory in the UK. And anyone can join this. There's no fee, there's no like prerequisite, there's no like you have to have a PhD, there's no you have to jump through an IAU hoop of like legitimacy, none of that. You can fill out a little thing on the website and join us. We have a Slack, we talk about all this stuff. We try to figure out how to deal with the observation and analysis side of things. There's also folks who are working on the policy side of things, the community engagement, as well as interfacing with various companies, the industry and technology hub. Lots going on there. Happy to talk about it more later. We also have a couple of folks in the audience I see over there who are members and heading up different aspects of this center. So if you have questions about that, that can definitely be part of our discussion later. So I also want to highlight that there is a symposium that the IAU CPS will be hosting coming up in October. The registration deadline is very soon. So if that's something you might want an excuse to go to the Canary Islands for, registering for that sooner rather than later would be recommended. I'm also happy to talk more about that. So SatHub has only existed for like a little over a year, and we're still kind of standing up some of our basic things, but this is kind of supposed to be the one-stop shop for coordinating all of your different needs as a more community-based thing where, you know, the Rubin is just a small piece of this larger issue. All right, so to sum up, the actual impact of satellites on Rubin science depends on stuff that's hard to measure. And that includes how many satellites there are, how they're orbiting, how bright they are, what the camera does when they're showing up in the images, and the software that we developed to deal with it. All of the mitigations presently to handle this from the satellite side are presently pretty much voluntary. So this darkness mitigate or brightening mitigation techniques and whatnot are not required at this stage. And identifying and masking the trails helps, but it's not going to rescue all of the science. Hopefully it'll, you know, make it workable in many cases, but it's not going to fix it all. And I also, we'll hear more about this as well during the session, but coordinating with operators is really, really, really important. And we need to have these good collegial conversations and they need to continue, but it doesn't scale well. Once you get like a dozen different satellite operators all trying to launch things at once and have their own constellation, that's going to be a heck of a lot of work for all of us. I think we're already on Zoom all the time. Woo! Rubin may have to dodge some satellites. TBD if that is actually a thing that we wind up implementing or not. But I think the biggest takeaway is that you need to expect ancillary effects as we are going forward and getting ready to have operations happen. There's going to be weird satellite fun facts that pop up and are going to affect your data and your science as we continue into this era of a rapid night sky experiment. So thank you very much. Do you want me to do the next one?
Yeah.
I think I figured out the right clicking order.
Yeah,
Right.
they're in tab order.
Brilliant.
Yeah.
Maybe.
Presentation
And
mode.
then,
See, now I've ruined everything.
Yeah.
Mouse is.
it's
Yeah,
very
it is
sensitive.
sensitive. Okay. So Ashley Vanderlee is going to talk about regulatory considerations. Ashley.
Okay. Great, thank you. So I work at the National Science Foundation. So I'm going to present kind of a perspective of what the Electromagnetic Spectrum Management Group has been doing to try to work in this area of the regulatory considerations and what we can do to mitigate. Now I wanted to start. Okay, it is a little slow responding. Let's see. There we go, we'll click. So this is really why you are all in the room right now, right? There's a science image, there's a streak. This is bad, right? This has ruined your very good science image. From a regulatory perspective, I think the three questions that we really want to consider are, when does that streak actually completely ruin your observation? So you have saturation, it's not recoverable. Maybe there was a transient that occurred, you're never going to get the information back. So to us, that's worst case. This we definitely want to mitigate. When is the satellite streak causing a nuisance? And maybe it's actually something with a lot of hard work, even with those nonlinear effects, maybe it's something that could be removed. So this is something that, you know, it's kind of a step B where, okay, maybe we can deal with it. It's going to be a challenge. You still want to reduce that as much as possible with mitigations, but it's something where we can put some effort. And then there's definitely going to be some cases where it can be easily mitigated. If you're not looking at transients, you're doing a deep stack. If it's only a certain percentage of images that have the streak, it can be easily mitigated. So with this in mind, I also wanted to mention, we're all here, we're astronomers. We say the streaks are bad, but we do have to remember that for many, those streaks are actually good. The satellites are bringing broadband internet coverage to a large fraction of the world that currently does not have broadband access. And so I think it's important to remember, you know, a lot of us, you know, if you're guilty of using a computer on an airplane or trying to access GPS on a hike, you know, this is why there is such a demand for this service from satellites. And so I think this is where, you know, really trying to work collaboratively to understand that there is a great good we're trying to do with astronomy research, but there is also a great good that the satellite companies are trying to provide with broadband and kind of getting to that point of equity. And this is not slowing down, right? There's far more wireless devices on the planet than there are people, and it's really not slowing down. And so this is just something to keep in mind, especially the issues around equity. And one other slide that some of the satellite colleagues have shown a lot, there's a lot on this slide, but if you just highlight on the circles, the white show the percentage of unserved households with broadband. And so in the US, we're close to 20% still unserved with broadband, which has sort of been a huge effort from the current administration. You look at South America and Africa, you're up to almost 90%. So this is an opportunity for a lot of folks to kind of leapfrog and get access. And so this is sort of the good that those streaks are causing. So that's something to keep in mind. When you do see these streaks in your images, this is where we have an opportunity to really try to collaborate, understand the good they're trying to provide, but try to work together. One other thing that we've noticed as we try to work on regulatory solutions is generally people in the satellite industry love space. They love astronomy. And so oftentimes they're not aware of the impact. So simply communicating to them, this is the impact, and really trying to work on technical solutions, we think can actually lead to mitigations and can lead to really good efforts down the road. And I'll describe some of those in this talk. So this was mentioned in the last two talks. This is where we're heading. Thousands of NGSO satellite constellations, mostly transmitting in the 10 to 50 gigahertz. That's where they're going to be providing the broadband internet. There's also a push to provide direct to cell mobile telecommunications. So that would push to lower frequency bands. One thing to sort of public service announcement, it would be helpful, I think, as a community that we also refer to these as large constellations and not mega constellations. Mega implies 1 million. And so that's something that folks have said, that is a exaggeration of kind of what's actually happening. And so that's, if we can be as precise as possible in the astronomy scientific community with what we're facing, I think it also really helps build credibility as we work with the satellite colleagues and with regulators and kind of in the international forum as well. So just quickly, some of NSF's responses to the new spectrum challenges. The main thing I wanted to emphasize is what's in red on this slide. Richard Green, who was the division director when I started, shortly after I started at NSF, was responsible for actually officially expanding the role of the spectrum management unit to include optical infrared impacts. And so this is officially kind of the job of the spectrum management unit, to advocate for the optical infrared impacts and not just the radio. So that's been, I think, a really important change. We also have, instead of 1 to 2 spectrum managers, we're going to have 4 to 5 coming up this year. So there's a lot of work, lots of coordination. So that's something just in terms of FTEs at NSF working on this issue. The other thing to highlight is funding. So the Spectrum Innovation Initiative, most of you are probably aware of this. It's hard to fund the kinds of things that sort of help facilitate science if you're trying to do just astronomy research, right? The astronomical division is not going to provide that. And so this program actually provides that facilitating kinds of research and work. So there's been some programs, including SwiftSat, to provide funding for coexistence between satellites and ground-based, including optical infrared. So continue to look. We're hoping that this opportunity will continue into the future, and that's a good opportunity if you want to do some technical work and do need some support. The other thing just to note is this is an issue across NSF, so we've been trying to also engage, especially the engineering and the computer science directorates, because there's questions about materials, for example, when it comes to building the satellite or designing it. It's not necessarily just an astronomy or a spectrum issue. Then maybe we can say, okay, what really is the challenge? Do you need a different design? Do you need a different paint? Do you need different materials that don't currently exist? So this is a place to also, I think, continue to work. A busy slide, the few things I'm going to highlight moving forward. Again, the things in red. We funded a number of workshops, and if there's other technical things that need to be worked on in the community, we're very open to continuing to fund more workshops, so reach out. That's a fairly easy thing to work on funding if there's a good idea. So that's something I wanted to highlight. And then also the coordination agreements. We facilitated 2 now with SpaceX, the first signed in 2019, updated in 2022. OneWeb was just signed in 2023. And we're currently actively working with Amazon Kuiper and hope to have that signed before the end of the year. Then I'll talk about those a little bit more as I progress in this talk. Real quickly, don't want to get into this in detail, but happy to talk later. The important thing with regulations is that basically there's very limited regulations in the near infrared and optical. There's some laser coordination safety standards, but the official regulations stop at 275 gigahertz. So if you go up to 3 terahertz, there's some identifications for usage, but there's no regulation that exists internationally or domestically where people have actually rights to parts of the spectrum. Of course, we want to use the whole spectrum, but this is kind of how the rest of the world views different parts of it. I wanted to mention there's 2 primary international bodies. So there's been a lot of work taking place in both of them. It's interesting, the International Telecommunications Union is what kind of manages that up to 3 terahertz and the allocations up to 275 gigahertz, but they're mostly focused on radio transmissions. They say optical, not in our wheelhouse, we're not touching it. And so, but it's important because every satellite that's launched actually does have to file with the ITU. And so there is going to be some discussions between the ITU and sort of other international regulatory documents and guidance that come out. The place where optical reflections and these kinds of issues, space debris are being handled is at the UN Committee on the Peaceful Uses of Outer Space and the UN Office of Outer Space Affairs. So there's kind of a loose liaison between the two, but just wanted to describe, this adds a piece of complication that you can't just go to one place to solve the problem. You have to kind of work on this in different areas. And happy to talk in more detail about this later. So I wanted to describe a little bit the history of the coordination agreements, how they came to be and how we've leveraged them to actually work and coordinate on the optical issues as well. So I mentioned there's the allocations that exist internationally. And then in the US, it's further complicated because we don't have a single regulatory agency. We have NTIA that helps with federal agencies and the FCC that helps with commercial. And then when there's disagreements, they kind of coordinate and work it out. The State Department gets involved when you take it internationally, but they kind of take the international rules and kind of boil it down to US rules that are mostly similar to the international rules. Here is the international and the US domestic table for a frequency band that is adjacent to the fixed satellite service, where a lot of the broadband is being provided by SpaceX, also by OneWeb. And the thing that's important here is the 10.68 to 10.7 gigahertz band is allocated to the radio astronomy service as primary. All other transmissions are prohibited. It's only for passive scientific use. In the US, there was a footnote that thankfully somebody put in years ago, US 131. And so this footnote says that for anyone that's operating this 10.7 to 11.7 gigahertz downlink band, you must achieve a mutually acceptable agreement with this list of observatories. Now, because NSF owns all of these observatories, that's where we took the lead in actually working on a coordination agreement with the satellite companies that wanted to transmit directly adjacent. And the reason you have to coordinate, obviously, is you can't, when you're transmitting, you don't have a perfect band pass. There's a little bit of spillover. So that's where you want to make sure that you limit that as much as possible. Now, the way that that's actually done, and I think there's some relevance going back to the first 3 questions that I asked about the optical streaks, is because it's not perfect, the way it's actually done is it's not 0 transmissions, because that's not possible when they stop right on the edge. But what is deemed to be acceptable via this sort of technical report at the International Telecommunications Union is up to 2% data loss is what has been agreed to for radio communications. So there's details of how this is actually calculated, but what this means in the end is that the average loss is going to be less than 2% for the satellite constellation, but there are parts of the sky where in the radio we're expecting up to 25–30% loss. And so I think you're going to see similar things with the satellite streaks, where maybe the average impact will be something, but there's going to be certain parts of the sky where you get a lot more of an impact. And so this is the kind of quantitative technical recommendation that I would encourage the community to work towards when it comes to satellite streaks. What truly is tolerable to achieve the science you want, and what would that recommendation be? So what would be sort of an analogous kind of recommendation or technical report to this that you might do for the optical? So then I mentioned the coordination agreement in 2019. It just really focused on the radio piece. In 2022, we had the update to essentially encourage SpaceX, and they agreed to work towards this. All of the recommendations that were put forward by the IAU CPS that came out of those workshops, the AAS. So this is where it's really important, all of the community recommendations, the things that you all are working on, NSF we just listened to, and that's what we put in the coordination agreement. So they did agree to try to work towards reducing the brightness to 7th magnitude, work on the attitude maneuvering, maintaining low orbital elevations, and providing the high precision telemetry. So I wanted to note that, there's many factors that do contribute to the overall scientific impact and the brightness. So there's lots of things the satellite operators can work on. So it's also good that we continue to encourage the astronomical community. What can we work on, right? So, it would be fantastic eventually if we could have detectors that don't have crosstalk or don't saturate at 7th magnitude. Maybe they don't saturate until 4th magnitude, but right now what we're stuck with is 7th magnitude is what we have, for the coming years. So there's a number of different things that astronomers can continue to work on. So this is another place to just encourage, the community to think about how can you mitigate so it gets to something where the streak is not, impacting your science, it just becomes a nuisance or something that can be eventually easily mitigated once we've solved the problem. So just 2 more slides here. Wanted to note that after the coordination with SpaceX, it became part of the authorization for SpaceX in their latest agreement. And then it was also added to the FCC Amazon Kuiper authorization. So essentially, they must achieve a mutually acceptable coordination agreement with NSF. And so similar to what I showed you before, we've put in those same recommendations that the IAU CPS and other parts of the community have recommended, trying to reach 7th magnitude, providing the high precision telemetry, all of those things. So wanted to highlight, I think this is good news. Amazon Kuiper is working very hard on some mitigations already, and we're hoping to have this coordination agreement within a couple months finished with Amazon Kuiper. So again, just wanted to highlight the work by the Rubin team. We really do see Rubin not as sort of the only telescope that we need to solve the problem for, but it really is kind of the test case. It's the deepest, the widest. So our perspective is, generally, if we can solve for Rubin in terms of getting the satellites to be not so bright, it's something that, a lot of other telescopes will benefit a lot from. So we've really been focused on Rubin, and the team has been fantastic helping to establish what these should be. And maybe I saw the poster yesterday, maybe we're down to 6.5 magnitude instead of 7th as being the criterion. So that's something would be great to see some more technical work on that. And also, this is a question I've asked a lot, but it's going to help with eventually when we get regulatory questions. What's the scientific impact with X number of satellites with a given size and a given distribution? At what point do you kind of pass that threshold where we're losing too much science? Because eventually, we're going to get those kinds of questions from the regulators. Is 50,000 too many? Is 100,000 too many? At what point does it really become a problem where you're losing science that you irretrievably can't get back? Again, wanted to highlight FCC has done an excellent job adding these required coordination agreements. So, hopefully we'll continue to see that. And also the 3 large satellite companies that we've worked with have also done outstanding work. Amazon Kuiper is the co-chair of the industry hub. So they put a lot of work into developing voluntary best practice guidance to share with the satellite community, not just the large companies, but also the smaller ones. You'll hear a lot from David Goldstein on all of the demonstrated improvements SpaceX has made. I got to visit the factory floor, and I'll tell you, it's not just something that they tell you in nice meetings like this. Employees on the floor all talked about, 7th magnitude is a design specification. It comes from the top, and everybody there is aware of it. So it's great to see kind of that level of commitment to working towards improving things. So we're really appreciative of that. And OneWeb is also committed, I think, in their generation 2, working towards getting to the fainter satellites. What can you do? Meredith mentioned a few things. I also wanted to mention, in addition to getting involved with the IAU CPS, there's the AAS committees on the protection of astronomy. And there's also a really important committee at the National Academies, if you haven't heard of, the Committee on Radio Frequencies. So we provide input kind of government only when there's FCC potential new rulemakings where we can say, hey, consider X, Y, Z. But the Committee on Radio Frequencies provides kind of public comments on the FCC filings. So this is a great committee to volunteer to actually be a part of if you have the time. If you don't have a lot of time, but you're interested in a particular filing, volunteering to do a little bit of work on kind of one particular study and getting involved with CORF would be really, really helpful. Because CORF, they file dozens and dozens of comments, and this is kind of the scientific community's voice back to the FCC that's been really productive. So with that, I want to thank you and happy to take any questions now or later. Thanks.
We have time for one clarification question. Okay.
If I may, Tony, I will point out that Francisco Forster has shared the paper that was mentioned earlier, Karpov and Peloton paper on the Slack channel. If anyone's interested, check it out there.
Thank you. Okay. So go here. Presentation mode. Even I can do this. Right there.
You're gonna drive.
Yeah, okay, I think we're ready to go. So this talk is from David Goldstein at SpaceX. It's remote. So Goldie, I'm gonna advance your slides and you're gonna talk and say next slide, please.
Okay, great, thank you. You can go to the next slide, please. Can you hear me okay?
I can hear you, but I can't advance the slide. That's interesting.
While Tony figures that out, thank you so much for the opportunity to be here today. I do very much appreciate, and SpaceX appreciates the opportunity to talk about Starlink. And yeah, the big picture wise, Starlink is making a big difference. We, SpaceX was founded to revolutionize space technology to point human beings towards being a multiplanetary species. And in that, we care deeply about space. We care about access to space, and we care about the sustainability of space. And it's in our DNA for what the company is all about. Starlink is an amazing constellation of satellites that's making just an amazing impact around the world. We support lots of communities that have not henceforth had access to high-speed internet, enterprise and small businesses, remote and henceforth unserved households and schools all around the world. And we're working as hard as we can to close the digital divide in the US and around the world. And I personally am super excited that Starlink is now offering service in Guatemala. There's a nonprofit I've worked with down there, and I'm working to get them Starlink terminals for internet at their locations and their schools. Super exciting. We are supremely committed to protecting the ability for humans to fly and inhabit space. And in that, keeping space safe for humans, keep it sustainable and accessible for everybody. You may or may not see this, but we actually launch our competitors' satellites. We want to make sure that people have access to space, and we don't triple the price on them. We give them the same price we do for everybody else. We're operating over 4,800 satellites right now in low Earth orbit, despite debris surges like Cosmos 1408 and other non-cooperative satellites that are operating in space. Our autonomous collision avoidance system does a remarkable job of seamlessly handling the debris that's there, and we've scaled and sized it for the future. And what you probably care the most about is that we will stand by our labor commitment to keep brightness reduced on our satellites, and also to ensure that we have the most accurate predictions available publicly so that anyone can access them, so that you can plan and predict where our satellites are going to be. Next slide, please. So as I said, 4,800 satellites in space, over 1.5 million customers served on all 7 continents. This 200 megabits per second is the current speeds, and we're pushing those speeds as best we can. Our Gen 2 system is really the key to be able to fulfill the orders that are out there and to really accelerate the deployment of Starlink terminals all around the globe. As part of our filings, and I probably should have had a slide on this, but I want to just make sure that everybody has a super clear understanding of the numbers of satellites that we're currently licensed for, and that we have applied for licenses for. So we have 2 licenses with the FCC, our Gen 1 and our Gen 2 systems. The Gen 1 system is 4,400 satellites in 4 different orbits from 540 up to 570 kilometers altitude, and with a few different inclinations. And so our Gen 2 system, we requested 30,000 satellites on our Gen 2 system, and we've been provisionally authorized for 7,500 on our Gen 2 system. So the total that we're currently authorized for is 12,000, about 12,000 satellites. And so those Gen 2 operational altitudes are from 525 up to 535, but we have some flexibility on the tolerance of where we put those. And so we're actually kind of packing them in tighter with our Gen 1 system. I'm happy to chat about that if anybody wants to talk about frozen orbits, but we sort of layer them in and spoon the orbits on top of each other so that we can pack as many satellites in as dense a region as possible. Again, back to keeping space sustainable and accessible. Next slide. So you've probably all seen this, and this is a little bit of a dated slide, but for a Starlink satellite, the main source of light that you see on the ground is from the incident light coming in, reflecting off the nadir facing deck of our satellite bus, and then reflecting down to the ground. And so I'll talk in a bit about the mitigations that we put in place to reduce the impact of that brightness on the ground and the visual magnitude of it. But just to make sure everybody has this in their mind, a visual magnitude 7 corresponds to an 8U CubeSat, which is roughly the size of, I have very large feet, so one of a shoebox that for my shoes, that's completely white, that's at 550 kilometers. And so the brightness targets that we're making are quite aggressive for the satellites that we're deploying. I think you'll hear Forrest talk a little bit about some other incident light that can be seen on the ground from Earth albedo and some other things, but fundamentally the light is reflected off the bus and or reflected off a solar array. Next slide, please. So in terms of mitigations, we really bin them in these 3 areas: hardware and satellite design. And so there are a variety of techniques that we've tried. We've flown thousands of shades that on our Gen 1 satellites, which I didn't mention this, but we have stopped producing our V1.5 satellites. And so there will not be any more launches of V1.5. Moving forward, we'll be launching V2 minis and V2s. Happy to take questions about that as well. We typically launch between 15 and 22 of those per launch, but they are about 4 times more capable than the V1.5. And so you can shade reflective surfaces. we can make the light so that it has a more specular reflection in order to reflect it away from the Earth. We can use dark materials so that any surfaces that are rounded or are at different angles can absorb the light rather than reflect it. We also pigment our solar arrays, and we have oversized our solar arrays on the V2 minis such that we can not have them perpendicular to the sun all the time, especially when there's going to be a brightness impact. And so we can off-point them so that we minimize the reflection from the solar arrays. So I think there was a study that someone mentioned where they assumed that the solar arrays were perpendicular to the sun, and we are not doing that with our second generation satellites. We also have included, and I'll talk about this in a minute, but we've included brightness mitigation as a design criteria at the start. And so it's not an afterthought like it was on the V1s. It was baked into the design early on. And so the main reason I mentioned that is because of the thermal piece. And so if you're gonna make components very dark with this absorbing black paints, then you need to be able to get rid of that heat. In terms of satellite operations, I mentioned off-pointing the solar arrays. We also can adjust the satellites as they approach the terminator to keep the reflections down, and we can bias the pointing if it looks like reflections are going to occur. And of course, we can provide we provide very accurate ephemerides on SpaceTrack. They're available publicly; anybody can get them, or you can use two-line elements. If you want the most accurate two-line elements, I would use those on celestetrack.org because those are actually fit to our propagated ephemeris, not to radar-based observations. Next slide, please. So in terms of the best practices, I wanted to just summarize this as quick as possible. The first one, talking to any other satellite operator, I'd say take it seriously and include it in your design criteria. And that feeds into this next bullet of the process that we use, which is you put it in your design criteria, you build hardware, you measure it, then you model it, then you launch it, then you measure it again, and you provide a feedback loop to the design. And working with LSST and others, it's been fantastic to be able to work with to get the measurements back and the precise times and location so that we can feed that back to our models. What we do is anytime anybody sends us measurements, we put in a database where we can overlay it with our model so that we can continue to work on the edge cases. Because typically what is seen when those brightnesses go up is edge cases. So to summarize all that, the mitigations are you reflect the light, you darken your sat, you shade, or you just avoid those reflections. And then, as I mentioned, continuously seek to understand those edge cases. And I really think that satellite owner operators, like the hallmark moving forward for every one of us should be to be transparent. Next slide. So in conclusion, Starlink is making a big difference. I really appreciated Ashley's slides there because we really take it seriously to make a big impact around the world, to keep space safe and sustainable, but also to follow through and mitigate the brightness to have it be as minimal impact on astronomy as possible. We do that by developing best practices, learning and feeding that back and being transparent about it. And if there's satellite owner operators that want to talk to us, you can have them reach out to me. My email address is Goldie, Goldy @spacex.com. And we'd be happy to talk to them, and we make our products available at cost. And then I will give a plug to NSF, and we really appreciate the strong partnership we have and the accountability we get there. And yeah, having agreements is the way that should be modeled moving forward. So I apologize for going a couple minutes over, but I can answer a question now or later.
Thank you, Goldie. Applause. So we have one Slack chat question.
I think Ashley was the only one that actually applauded though. I could hear the applause. No, I'm kidding.
Can you hear us?
Yes, I can.
Excellent. So we have one Slack question.
Okay.
Marcio Catalan writes, does anyone know if there are ongoing conversations between our community and AST Space Mobile as well? Their Blue Walker prototype's maximum brightness is completely off the charts, reaching visual magnitudes around 0 or so. And my understanding is that some of their satellites will be even bigger and brighter. And I see some responses from Meredith. Do you want to comment?
I mean, I will comment, and we have talked to them about brightness. We've offered them our dielectric mirror film, and we have shared, you know, intimate details about our best practices with them.
Yeah, sure. So we are in touch with some folks at AST Space Mobile as well. I'm not sure. Connie, do you have any newer updates on those discussions?
Wait.
Oh, hang on.
My apologies. This is Connie Walker from Marlab and the center. Yeah, we've had a very good initial contact with them when we had initially had our first draft of the paper. We wanted to make sure we're not saying anything that would be against what they felt would be correct to show the public. And they were looking into mitigation solutions for the future renditions of, this is just a prototype, but the future ones, there's like 5 new ones coming out that are going to be bigger, and probably if they weren't going to do any mitigation, would have been brighter. We have to follow up with them, so that's still an ongoing process. And then of course after the 5, I think they're going to have others too, and I'm not really sure as to the details what they're like.
Yeah, ongoing is the short answer to that question.
So we're going to hear next from Forrest Fankhauser about software to predict optical satellite brightness.
Oh, you already got it right.
No, it doesn't advance.
I think you just got to click.
What did you just do?
I just clicked the screen. I
Okay,
think it's
okay, great. Forrest.
All right. Hi, everyone. Thanks for coming out this morning. My name is Forrest, and I'd like to talk about a new method for predicting the optical brightness of satellites. So obviously everyone has their own slide about brightness mechanisms, but basically when sunlight hits the satellite, if the satellite is near the terminator, that light can be scattered onto observers on the nighttime half of the Earth. Most of this talk is based on our paper, Satellite Optical Brightness, which we just published. And in the paper, we do discuss Earthshine, where light scattered from the daytime portion of the Earth's surface is scattered by the satellite, but it turns out to be a fairly small effect, and I'm just going to leave it off the table for this talk. And I want to start with one of the most useful parts of our paper with respect to thinking about satellite brightness. Let's see. Is that better, Tony? Okay. So we actually came up with this reference frame, which we call the satellite centered frame, or I sometimes just call it the brightness frame. And it's really helpful in reducing the dependent variables that we think about with respect to brightness. So in this reference frame, brightness distributions are only a function of the satellite's height and the satellite's angle past the terminator. And this is really helpful because most LEOsats operate in circular orbits. So you can make some metrics like peak brightness or average brightness on the night sky a function only of the satellite's angle past the terminator. Which I think is really helpful. And then I would also just throw out that this reference frame is very intuitive, and you can answer a lot of questions about brightness using like hand calculations and high school geometry. So I would just really recommend that you at least try using this in your future research. So I want to talk about how we decided to model satellite brightness. ray tracing is sort of the obvious solution, but it's not a good choice because it's computationally extremely inefficient. So instead what we do is we add up the bidirectional reflectance distribution functions of every primary surface on the satellite. So the BRDF measures the scatter properties of a surface. You could have a shiny piece of aluminum or a diffuse piece of paper or anything in between. So this BRDF measures those different material properties. So you can see here we have the BRDF of the chassis deck and the solar array for Starlink V1.5 satellites. And what we do is we actually fit measured BRDF data to analytical, empirical BRDF models. And then we can use those models to calculate satellite brightness at an observer. And you throw in like an inverse square law and some cosines, go read the paper. The details don't really matter. And I think what's really interesting is we actually found two ways to get these BRDFs, which are both really useful in their own right. So one way, which we're showing here, is you can just take laboratory measurements of the surface to get the BRDF. And so SpaceX provided these measurements, which we were able to fit. But then sort of after we had already done this, we realized if you have enough observations of satellites on orbit, you can sort of indirectly infer the BRDFs of the satellites. So this is really helpful because it gives us an avenue to calculate satellite brightness when constellation operators aren't feeling cooperative. So I'd like to just get right into talking about our results. We decided to validate our models using Starlink V1.5 because there's plenty of observations out there. And we had great collaboration with SpaceX to get some of the numbers we needed. So our brightness model consists of two primary surfaces. We have the solar array, which mostly drives backscattered light. So that light is going to be more visible for observers near the terminator. And then we have forward scatter from the chassis deck, and that's going to be visible to observers farther into night. So I want to start with the old brightness calculation method. This is the diffuse sphere model, and I'm a big proponent of just throwing it out. It's sort of, physicists love a spherical cow model, and this is that for satellites. It's not very physically based, but I'd like to use it for the sake of comparison and sort of explain these plots. So we have the sun altitude increasing from left to right, and we've fixed the sun azimuth at 90 degrees. So you can think of this as what an observer is going to see if they were standing at the equator during sunrise. And the color shows the brightness a satellite would be if it was at that point on the sky. So the center of these plots, that would be straight overhead. And then the top of the plots is going to be the northern horizon. And to the left, you have the eastern horizon. So you can see the spherical model is quite simple. And satellites these days are a lot more complicated than this. Maybe it worked for asteroids, but here's our new improved model. So this is our model with laboratory measured BRDFs. And you can see that as compared to the diffuse sphere model, we actually have two separate lobes of brightness. So deep into night on the eastern horizon, you can see that light being specularly reflected from the chassis. And then as the sun rises in the western sky, you get this lobe of brightness backscattered from the solar array. And hopefully you're already thinking about the applications to LSST. I mean, you can imagine streaks that get bright and then dim and then bright again, and we're going to have to be able to handle those cases. Next, I'd like to also show our model where we fit our BRDFs to a bunch, like 2,000 satellite observations from the Pominus Observatory. And you can see that it's sort of in between. I don't have a great way to back this up, but I don't think this is quite as accurate as the lab BRDF models. But luckily, we are still getting some of the features we're looking for. So we have forward scatter from the chassis and backscatter from the solar arrays. And luckily, we can back this all up with data, once again, from the Plominus Observatory. So what I'm plotting here is we have the measured AB magnitude from the observatory versus the calculated AB magnitude. And you can see that our model with lab BRDFs has fairly good correlation, but it systematically underpredicts brightness since we're not modeling every single component. We only take 2 primary surfaces. And then as expected, our model that's best fit has fairly good correlation and fairly good bias. And then you can see that the diffuse sphere model doesn't have great correlation and is not physically based. And I just want to highlight that the V2 satellites will not have this contribution from the solar array as strongly since they're off pointing the solar arrays, which will actually make this diffuse sphere model less and less accurate. So I think, expect this correlation to be even worse in the future. And that sort of highlights the need to move to these new models. I'd also really want to drive home that our model with lab BRDFs has no on-orbit measurements. So we actually can make a correlation like this for a satellite which doesn't exist in space yet. So that brings me to some of the applications of this paper, which aren't fully thought out. But one that I'm really excited about is trading satellite design where brightness is a constraint. So SpaceX actually used this computational technique to inform brightness mitigation for their V2 satellites. And what's really great about this is unlike any of the other satellite brightness modeling attempts I've seen, we don't require any on-orbit observations. So you can get this feedback loop where you're going from design to brightness calculation and back without ever sending a satellite to space. And then of course, we can predict satellite passes more accurately. So this is for Tucson tonight at 10:30. And we can predict fairly accurately that we should see a peak brightness of 5.3 AB mag in the eastern sky about 45 degrees above the horizon. And then you can obviously extend this to LSST. I want to emphasize that this is a toy constellation model with 30,000 satellites and a toy brightness model meant to represent Starlink V2, but this isn't published. Don't take this as absolute truth. And so we looked over a period of a 60-second exposure, and we see these 7 streaks visible in the detector. And I think what was especially interesting about this analysis is we see that the brightness of streaks can vary by a factor of 2 across an image. So that already kind of informs you whatever streak removal algorithm we have needs to handle this case. And then I think going forward, Tony's group is working on something really exciting where we combine satellite brightness models, a constellation model, and the LSST observing schedule to generate images with satellite streaks and without satellite streaks. We can then pass both data sets through the data management pipeline and come up with overall scientific impacts of satellite constellations. So this is kind of what we're looking for regulation, where you can say, if you have these 50,000 sats with this brightness distribution, here's the science we would actually lose. So for our starting effort, take a look at Fan's poster. It's really interesting. That's all I have for today, but if you're interested in this, please check out our paper. And I'd also just like to say that none of this would have been possible without collaboration between SpaceX and our astronomy team, and I would really like to see more of that collaboration in the future. Thank you.
Okay, thank you, Forrest. We have one more talk from Adam Snyder on satellite streak masking challenges. Let's see. Oh, yeah. And whoa. Okay. You're good.
That's the last part.
Yep. Right. Hello, everyone. I'm Adam Snyder. I work at UC Davis with Tony Tyson. I'm here to talk about sort of broadly the challenges that face detecting and masking streaks in images. So I hopefully everyone's got a chance to take a look at some of the posters that we put up. In particular, we have a poster talking about crosstalk. So this is very much focused on what we call the secondary streaks that appear in our images as a result of the primary bright streak. But this talk is going to focus more on what is necessary to identify and mask the main trail, which will still exist even with this crosstalk correction. So the wings of the satellite streaks after masking will have surface brightnesses that are comparable to the faint galaxies in LSST that we call the gold sample. And if we're not careful about how these satellite streaks are masked, we will introduce systematics such as resulting from the residual spillover light. So you can see in the plot, there's a little bit of light that can be left depending on how big your mask is. And also this phenomena that we've found we call lines of bogus galaxy detections that can occur from these incompletely masked streaks. So one thing that I found is that the surface brightness profile of these satellites can vary dramatically depending on a number of factors related to the magnitude of the satellites and both their geometry and their orbital parameters. So I've plotted here 3 different cases ranging from sort of contemporary size satellites and then projecting forward to larger and larger satellites. So from 3 meters to 50 meters diameter satellites, you can see the surface brightness profile can vary quite a lot, especially as larger and larger satellites become more and more defocused. They will spread out and make the sort of plateau surface brightnesses. I do have some simulation tools that I've developed. It's available in this GitHub that I've linked here. It's currently a work in progress, and I'm working pretty hard to improve it. But this is what I use to generate these profile plots. So the challenge that we're faced with is that it's very difficult to determine exactly how we should mask these satellites. There's the variability of the streak profiles and variability of mask widths. And if you're not careful about how you pick your procedure, including how you assemble coads or how you do your source detection, you can it can result in the detection of a number of bogus galaxies that will be oriented along the 2 streaks. So we decided we would study these using sort of a toy model of simulated 10-year coadded images. So this pictured here is just a 10-year G-band coadded frame where I've incompletely masked the satellite streak. So you can see the residual lines. So the goal was to basically see under what conditions would we get these bogus galaxies to occur. So I've included in the next couple of slides, there's a couple of examples where I've blurred a coad by the PSF, ran source detection with a 5 sigma detection threshold, and found where these bogus galaxies occur. So here's a 3-meter diameter satellite with an 18 pixel wide mask, where we've got 2 circled or 2 bogus galaxy detections that were found by the source detection algorithm. Here's another example with a 10-meter. You can see the satellite streaks are getting farther apart because our masks are growing. This has got 3 bogus detections in it. And I also should point out the range in the color scale is only 2 electrons. Right? It's actually less than 2 electrons. So these are very, very small elevations above the noise background. And then finally, here's a 50-meter diameter satellite example with a very large 76 pixel wide mask where we've found 2 bogus galaxies. It is kind of fortunate that the bogus galaxies that do occur under different conditions do seem to share similar properties in terms of their ellipticities and their fluxes. They are all elongated along the streak, as one would expect. They're largely, E2 is very much Gaussian distributed around 0. So these populations, if they do occur, share many similar properties. And while it can be, it's relatively simple to filter these out, one thing we were concerned about was what happens if these bogus galaxy populations begin to pollute your samples of real galaxies. And in particular, if they lie close enough to true galaxies, you can have blending between the real and the fake and the bogus galaxies. And this we were concerned about as possible impacts on shear correlations, because now you have this line of fake galaxies that are elongated in particular directions that begin to impact measurements of real galaxies. So this is some work that it's still preliminary, but we were able to generate an LSST-like catalog of galaxies from an n-body catalog of billions of galaxies. And then using the distributions of the properties of the bogus galaxies, emulate real plus bogus galaxy blending by injecting these galaxy populations and drawing from the distributions of ellipticities and fluxes. And then recalculating magnitudes and ellipticities of this now blended and polluted population, running it through a cosmological analyses and determining impacts on parameters such as S8 and sigma 8. So as you can see here, we've already seen, given almost a very large pollution of your galaxy sample, that you begin to see small impacts on measurements of these cosmological parameters. Another thing, so I guess to summarize, we're sort of faced with three different challenges. We need to be able to identify the satellites and individual visit exposures. So this is basically addressing challenges to linear feature detection. We haven't talked about that much, but it's been touched on a little bit. You know, the first step is finding where the satellites are. The second is determining how we decide to mask these objects. They must be masked in such a way that we can prevent the occurrence of bogus galaxy detections. And of course, there are other parameters that go into their occurrence. So we'd like to study these in more detail to make sure that we can prevent them in all cases. And this is further complicated by things like satellite glinting or variations of the surface brightness profile. So Forrest talked a little bit about that, how a single streak across the focal plane can vary in brightness, and depending on those scales of variation, could contribute to things like bogus transient events. And you know, being smart about how our mask is created such that it can account for these variations. So I think that's all I have. I'm open to any questions.
Okay, so we have a few minutes for discussion. Rachel, did you have somebody online, or should we go? Is there somebody in the room? Actually, we should go to the room first and see if we have a question in the room. A couple back there.
Yeah, I have a couple questions. First one, maybe either for Adam or Meredith. Do you have an estimate of what fraction of the pixels need to get masked for to get rid of all the satellite trails? Like, what's the?
It's a very small, I can answer that, I think. There's a very small fraction. Personally, I'm not worried about the lost real estate.
Okay.
Because of that, except for one edge science case, which I think is important, mainly follow-up of gravitational wave events. But I'm more worried about the fact that LSST, for all of us, at the end of the day, is going to find something unexpected. And it's going to be new, and it's not in our science book. And this is unexpected stuff. And we have tails of distributions overlapping statistically. And I think we're going to be systematics limited. And it's the systematics that are introduced by all of these incomplete things that we're trying to do and software to get around the problem.
Okay.
I have a question for Adam. I missed
I
something
still had another
important.
question, if you don't mind.
Oh,
Sorry, I had a follow-up question
sorry.
for Adam. So Adam, when you were propagating to cosmology, were those galaxy detections from coads, or were they single? Because I would be very surprised if those, you know, spurious galaxy detections survived through the coadding process.
I believe they worked through coads, but it was single filter. So the hope is that if you're combining filters, then yes, they won't align with with fluctuations in the other filters, and they'll be removed.
They shouldn't align with any other observations because they're single observation artifacts.
Yeah, so when I created the COAD, I did not do any sort of more advanced filtering of the pixel images when I created them. I maybe should have made this point more. We really were interested in seeing under what conditions, and if they did these would occur, and if they did occur, what they would look like. This is sort of a worst case scenario. The hope is that if you're doing, some smart sigma clipping or median stacking, that you would be able to remove them, but they can contribute to elevating the tails on the distributions of the pixels and maybe introducing some even more subtle effects.
Yeah, the bottom line is nothing's perfect. So we'll have these bleed through events, even in the COAD.
My question was actually quite similar to the previous question. I think the main reason for these artifacts appearing in COAD is that simply the width of the mask was too narrow. You increase that mask by 50% and there are no problems. You can show it almost analytically. And as Tony said, the fraction of pixels that we would lose is tiny. It's smaller than the chip gaps that we have in the camera. So in this particular context, I think we should not overemphasize problems when they're not that serious. However, I do agree with Tony that we need to be very careful about unexpected things, glints, impact on alerts, etc. So I am concerned like everyone else about these satellites, but let's not make it bigger than it really is. In particular, let's not make it sound larger than we can quantitatively justify. And when, as a project, we want to talk to other entities, we should all use the same numbers and make the same statements. And there will be very soon a technical document from Peter Joachim that will also compare to these other studies that we will use as project when we talk to other entities. We need to use the same numbers. We cannot.
Yeah, I agree with you that if we can detect the satellite streak and detect all of it, then being very conservative in the mask is the way to go. And we showed that in a previous publication. But nothing is perfect. And we found that not all satellite streaks and not all parts of satellite streaks are detected in the DM software.
Hi, two questions. One for the astronomers. I see a lot of emphasis on the sunlight, but what could happen with the human sources like cities, mining on the Andes, and also the fleets on the southern oceans? Maybe they are very low luminosity strike, but how this could affect the low surface brightness galaxies and also time domain variability?
Yeah, so in Forrest's paper that he gave you a reference to, we discovered pretty much at the last moment that cities in South America are fractal in terms of their light distribution, and that comes up and reflects off of the shiny bottom of the satellite down into your telescope. And they average between 14th and 17th magnitude. Even brighter, yeah. So that may or may not be a consideration, but it is a time varying thing because the satellite's moving across the sky.
Right. And for the regulators, the question is about what will happen with the low frequency radio wavelengths in terms of protecting the below 200 megahertz, this the window to access the very early universe. The people are building bigger arrays, interferometric arrays, and here it's not a strike, it's the beam of the satellites. What are the measures? There are some measures taken on this sense.
Was that for me?
Yeah, if you want to take it first, Goldie, and I can fill in.
Yeah, why don't you go ahead?
So there's a couple things. The frequencies that they're actually transmitting, one of the things that we have started to work in the coordination agreement, for example, with SpaceX, is that they're actually going to work to avoid main beam illumination where we actually have radio telescopes. So that will actually reduce the brightness. They don't have to based on the regulations. It's their frequency spectrum, but they are taking those steps. So we've done some initial testing at the VLA and also at the Green Bank Observatory. And it does seem to help when you actually avoid that main beam illumination. There's still side lobes, so it's similar. You're still going to have some impact. I'm also aware of some of the spurious and out of band, like unintended emissions. So this is similar to what like the SKA measured recently, and similar to what this kind of back and forth that we've been discussing here in the optical. I think when those issues were raised with SpaceX, they immediately went to figure out, where is this coming from? Is it something that can actually be mitigated? So similarly, sometimes there can be filters put in place because those kinds of emissions are not actually, it's not a licensed transmission. So, it's something that everyone's going to work to reduce any kind of out of band or harmonics or spurious. So I think that's going to be sort of step by step. One thing that is important is that telescopes around the world establish radio quiet zones. And that has to be done on a country by country basis. South Africa has one. Chile has an area as well. And so really working to try to coordinate, especially for quiet zones, that we can actually encourage the satellite companies to avoid that main beam transmission as much as possible. And that's possible at the higher frequencies. It's harder when you get to the lower frequencies, where a footprint can actually be a third the size of the Earth. At these higher frequencies, 10 gigahertz and up, the footprint is 40, 50 kilometers. So you really can avoid main beam illumination.
Thank you, Ashley. I think we have an optical question on Zoom.
Yes, so there have been several questions, and thanks for Meredith and Ignacio for responding in real time. We have one question from Claire Saunders. I would like to comment that the examples of satellite streak masking shown from Hassan et al. 2022 are not representative of what is actually done in the Rubin science pipeline. We are masking a significantly wider band than what was shown. Additionally, the catalogs that are produced will come from coads of many measurements, so any remaining effects will be much lower.
Can I make a comment to add to that?
Please go ahead.
So I just wanted to say that the examples shown from the Hassan paper were giving a purposefully narrow mask to the satellite. So what is actually going to come through is really not at the level of faint galaxies. We're cutting below the background noise level. But additionally, like if people are looking at data that's coming through the DM pipelines and see satellites that are still there, I will say we do need to have at least 3 exposures on the same place to do the satellite masking. But if we have at least 3, we should be able to do a good job. And if you're finding things that come through, like definitely tell me, because I actually don't have any examples where we're failing to find and mask satellites in those conditions. And, I'm definitely open to anything we can do to improve the algorithm, but like as it is, we're pretty much getting 100% where we have sufficient data. So this is where I kind of need help from the community to find edge cases that are not being covered.
Yeah, that's a good point. We're not finding that success in the lab, so maybe there's something different. Anyway, this is near the end of the session. Maybe Richard, you have one question?
Well, I do. We've been asked, at least by some operators, what are the prospects of defining what I would call a structure function, namely, what are permissible frequencies of flares and glints as a function of their relative brightness compared to DC? And so, your simulations are making excellent forward progress on the DC level. What are the prospects of our giving them that kind of information, where a 0th magnitude glint never, a 2% fluctuation, well, we tolerate, what are the prospects for understanding what science?
Yeah, I think the time domain is the next frontier in these full simulations. And actually, it's probably more interesting scientifically, in my view. Because there's going to be a lot of these glints. And they will form a foreground haze of noise in time domain work. Okay, well, thanks, everybody. That was a productive session.